So today's topic is right triangle trigonometry. And the idea here is what we learned on the unit circle actually can help us to solve triangles. Any right triangle has the following setup. Suppose I label it like this. I'll put A here, B here, and C here. You can interchange A and B, that happens a lot, but C should always be the hypotenuse of the right triangle. And then I'll put angle beta opposite B always, and angle alpha opposite A always. So the legs are A, B, the hypotenuse is C, alpha's opposite A, beta's opposite B. And you say, I wonder what the trig functions of this angle in the triangle are based on our definitions in the unit circle. Well, it's not hard, actually. You can use the triangles principle that we've discussed before, and we can fit this into a unit circle. Suppose this is the unit circle, radius 1 here. Then what do we know? We could construct this triangle within the unit circle that's similar to the triangle we have, right? We just, oops, not this one. This one, drop a perpendicular from where this side of the triangle intersects. And now, since this is on the unit circle, the coordinates of this point here must be cosine theta and sine theta. Cosine first, except it's theta. And you can see they're similar, right? They have this angle in common, so they have one congruent angle. It's the same one. But the 90 degrees here and the 90 degrees here are the same, so they have two angles the same by the sum of angles theorem, right? This one must be the same, and they're similar. So these are similar triangles, and now we know, since this is radius 1 on the unit circle, that sine beta, this side, is equal to the y-coordinate over 1. But the y-coordinate over 1 is the same as b over c because they're similar triangles, right? What we've shown is that in any right triangle here, the sine of the angle beta is equal to the side b over the side c. Right? We can also compute the cosine of beta, right? The cosine of beta from the unit circle is the x-coordinate over 1, or just x. X-coordinate or x over 1. But that's the same as the ratio of this side to this side on the other triangle because it's similar. Oops, this side to this side, so it's a over c. What we've shown then is that the cosine is just a over c. Well, more suggestively, we could write it this way. Since the side beta, well, I can't talk today, b, is actually opposite the angle beta, right? It's not helping form beta. We could call this the length of the opposite side divided by the length of the hypotenuse, right? And similarly here, we could call this the length of the adjacent side of the triangle, the leg that does help form the angle, divided by the hypotenuse. What we've got now is for any right triangle, sine beta is equal to the length of its opposite side over the hypotenuse, and the cosine of beta is equal to the length of the adjacent side over the hypotenuse. Similarly, if we go to construct the tangent, we know that's supposed to be y over x, but y over x in the unit circle is the same as b over a in the triangle, which is the opposite side divided by the adjacent. Now, by the reciprocal identities, or by doing the same thing in the triangle, it doesn't matter. We can just turn these upside down and get the other three. Cosecant must be this upside down, since it's reciprocal of sine, is hypotenuse over opposite. The secant, being the reciprocal of the cosine, is the hypotenuse over the adjacent. And the cotangent, being reciprocal of tangent, is adjacent over opposite. These are the 6 triangle relations. That's the proofs. Maybe I should box them out here. And say that is, we just proved a theorem using similar triangles. All of trigonometry is based on this idea that every right triangle is similar to a right triangle in the unit circle. And so you can just have these relations always. Sine beta is always the opposite side over the hypotenuse, no matter what size the triangle is. Right? Cosine beta is the ratio of the adjacent side of the hypotenuse. And you may have seen these in algebra at the end. Sometimes they teach you a little trigonometry. And I'll point out again that in many books, they actually introduce trigonometry as ratio of sides of triangles, and then they generalize it to the unit circle. They do it the other direction. This book chooses to define it in the unit circle and then take a special case of these things in the triangle. So here's what we have. Sine, the tangent of any angle is the opposite over the adjacent. And then the others are the reciprocals, right? Cosecant is hypotenuse over opposite. Secant is the hypotenuse over the adjacent. And cotangent is the adjacent over the opposite. So there is the relations for triangles. Here's the big point out of this. These, let's call them equation 1, allow us to solve, meaning find all angles and sides, any right triangle given any 2 pieces of information other than just angle. If I tell you 2 angles in a right triangle, I've really only told you one thing, right? Once I tell you this angle is 30 degrees in a right triangle, I know this one's 60. If I tell you it's 20, this one must be 70, right? They're complementary. So given 2 independent pieces of information, one side and one angle, or 2 sides. Believe it or not, we can now solve the triangle, find all the angles and sides, just using these trigonometric relationships. Okay. So here is an example problem, and we just need to do each of these cases. And it's kind of like a cookbook, a lot of this. You saw last time that we said there are these different cases you want to be able to find all trig functions. If you're given a point on the terminal ray, you want to be able to find all trig functions. We showed how to do that. If you're given a special angle, you want to find all the trig functions exactly. You want to be able to do that. Those kind of things. If you see this, do that. If you're given one trig function and a quadrant, we can find all trig functions exactly. So those are the exact cases, and other than that, you find it in a calculator. Similarly, we have kind of a cookbook approach here. If you're given an angle and a side, you have an approach here. And if you're given 2 sides, you have an approach. And you just practice a few of these till you know how to do them. So here's the first case. I'll just pull it. Yeah. Okay. Suppose I'm given this triangle here, and I say solve for the triangle. The problem on the homework says solve for the unknown sides. I'm going to find the other angle also. But suppose this is a special triangle, 30 degrees, 90 degrees, and then the last one follows at 60 degrees. And suppose this side length is 7, and I call this C, and I call this B. And I say solve the triangle. You could actually use the similar triangles that we did at the beginning of the course, but we'll do this one with trigonometry to show how you can do this in general. Solve this triangle exactly. Well, what you do whenever you're given a side and an angle, measure, is you write a relation relating those two things that you know and one you don't. So you write a trig relation, one of those six, relating the two knowns, one unknown. That way you can solve for the one unknown. And we could say, for instance, there's different ways we can go. The tangent of 30 degrees is opposite over adjacent. How about that? Tangent of 30 degrees is equal to 7 over b. Using the tangent relationship, tangent of an angle is its opposite over its adjacent. So you take the side that doesn't help form it, the opposite side, over the adjacent one, the one that does help form it. Since I've got two numbers I know and one I don't, I can solve this, right? Just easy algebra. Now there's lots of ways to do this. I think the easiest way on here is just take reciprocals. If these are easy, then I can take reciprocals and say 1 over the tangent of 30 degrees is b over 7. You might say, well, why didn't you just put cotangent equals b over 7 in the first place? The answer is yes, I can certainly do that. But on your calculator, when you go to do these later, what's on the calculator is sine, cosine, and tangent. The other ones, they just figure you take the reciprocal, 1 over these when you calculate on the calculator, so you don't need those extra buttons. So I usually like to write these in terms of sine, cosine, and tangent, so that if I need the calculator, I've got it. I don't have to do the extra step, but certainly cotangent works here too. So we take reciprocal equals reciprocal, since these are equal, and now you multiply by 7 and get 7 over tangent 30 on the left equals b, the 7's canceling on the right. I just have to be able to calculate that. And because 30 degrees is a special angle, I can calculate it exactly. I think of the unit circle in my head. What if I have a 30-degree angle here? What's its tangent? I drop the perpendicular. I know the sides are 1/2 square root 3 over 2. And I can observe the tangent of 30 degrees is y over x is 1/2 over square root 3 over 2. The 2's cancel. Oh, it's 1 over square root 3. So I can say immediately, putting that in, 7 divided by 1 over square root 3 is b. Well, 7 over this number is equal to 7 times its reciprocal, so we have 7 times square root 3 equals b. There's the exact number on that one. When you get a special triangle, one with special angles, right? Then I want to be able to solve these exactly like that. That's step 1, though. I'm solving the whole triangle. That only finds that one side exactly, right? This is b, sorry. Is exactly that. Now what's c? Well, I can say at step 2, by the Pythagorean theorem, solve for the hypotenuse. C is the square root of a squared plus b squared, right? That's just the Pythagorean theorem. I told you we'd use this all semester. If I start with the Pythagorean theorem, I gotta subtract and square root, or at least square root on this one. It's easier just to start with a solve for c, so I'll do that. This is the square root of, let's see, 7 squared plus 7 square root 3 squared comes out to be square root of 49 plus 147 gives square root of 196 or 14. So there's trigonometry to solve for the other side. And now the last one, the easy one, is to find the last angle. We could have done this first. In a right triangle, remember these angles are always complementary. They add up to 90. Right? So if this one's 30, this one has to be 60. So we can write immediately now that, let's see, this is beta because it's opposite b. Beta must be 90 minus the other angle, 30, must be 60 degrees. Now, if you're very astute, you might have realized something, that there was another way to do these special triangles. When you have a special triangle, we already talked about how you can do these in the first part of the class. Their ratios are always 1 to square root 3 to 2, right? This is the first triangle. We have 1 square root 3, 2, or you can have the one that fits in the unit circle, 1/2, square root 3 over 2, and 1. And so actually, once I know the short side here, 7, I know immediately this one is square root 3 times that, and this is twice that, right? That 1 square root 3. So if this is 7, this is 7 square root 3, and this is 14. I could have figured just by similar triangles from the beginning. But I still say that this will be useful in the later things to be able to do it the trigonometry way. So this is the hard way. Nonetheless, it shows the way that if these weren't special angles, we could still compute this in decimal form. But that's the 1, 2, 3, given a side and an angle. One, use a trigonometric relation relating two numbers you know and one you don't to get another side. Use the Pythagorean theorem to get the last side. Use the complementary angles theorem to get the last angle. You've got it solved. Right? It works every time. This is a really useful technique if you're out in lots of places. You want to know, ever done the golf course thing, and you can maybe measure an angle here approximately, and you know how far it is over here. So you know this side and this angle. I wonder how far it is here over to the golf hole. Right? Something. So all those kind of problems come up all the time in your backyard with your garden or something. There's lots of times where you need to solve triangles. All right. Let's do one more of those, but this time it won't be a special triangle, so we'll see the same technique. What you need now is a calculator. And here's the next problem. Suppose we have, this is 5A on the homework, this triangle. Suppose the right angle's up here. And this is 10. And this is A, and this is C. And this is angle alpha. They call it big A on the handout here. And this is 62 degrees. All right. Once again, solve this triangle. But now it's a non-special angle. Give it an angle and a side. You do exactly the same thing. But this time I don't have, since it's not a special triangle, I don't have the shortcut. So the same steps. One, I can use the one trigonometry relation. For the two numbers that I know and the one I don't. So here's an angle here, and I know this one, so I want to relate it to another side. Let's relate it to this side. We'll say this side is opposite the angle, and this is the hypotenuse opposite the right angle, so it's sine 62 degrees is equal to the opposite over the hypotenuse, right? The numbers 10 that we know and C that we want to find. All right, sine 62 equals 10 over C. Now I can solve it for C. Once again, since C is on the bottom, we can take reciprocals of each side. I'm going to do it a different way this time, because I'll emphasize here, a lot of you learn different ways in algebra. Another way you can solve this is multiply both sides by C and say this is equivalently C times sine 62 degrees equals 10. So that's an algebra step instead of taking reciprocals to this. Then divide by sine 62 and get C equals 10 over sine 62. Right? Canceling this on the left and dividing on the right. So there's the way to solve, another algebra way to solve it. Do the one that you're used to so you don't make mistakes, right? Since I don't know what the sine of 62 is, I have to run it on the calculator. And here's an important point. I usually bring the calculator back in here and we do it in class, but I really can't hand them out this semester. It's not safe. So we'll just show it on here. And if you get to class and you really want to borrow a calculator, we have something you can borrow briefly. I can't take them home, but you can play with them here. Let's see. And now to calculate the sine of 62 degrees, here's how you do it on this calculator. I can't show it up close, unfortunately, but you push on here, there's a button that says SIN for the sine after you put it in degrees mode. So you first push mode on your calculator to check that it's in degrees mode. Otherwise, they'll take 62 as radians, right? So mode is up here on my calculator. And then if it's not got degrees highlighted already, then I arrow down. There's a whole bunch of things you can set, right? You can set the number of digits to display, and there's a clock on here and everything else. But I'll arrow down and select degree. Every calculator has a mode changing thing like this, and it's usually pretty similar. There's usually a mode button, but this is a TI calculator. You probably get it in high school or something. Mode, select degree, then push enter. Let's put it here. And that changes the mode to degrees if it wasn't already. If it's already highlighted, you don't have to do anything. Now you just push second mode, because up above mode it says quit. And so that gets you out of the mode changing thing. Different calculators are different. Even the TI-89, I think you have to push enter instead of second quit. And other calculators, you get out of mode differently. If you push the wrong button, like if you push escape, then it drops that you changed this and puts it back in whatever mode it was before you did this. So sometimes it's good to go back and push mode again and see if it really changed it to the right mode. But this is how you do it. Mode button once, arrow over to select degree, push enter, so degree is highlighted, then push second mode to quit. All right, now once it's in that degrees mode, you just push sine. Most calculators today insert double parentheses, and you can just enter the angle between it. We'll do the 62 degrees. But some calculators, like this old one, you have to put the closing parenthesis. It only inserts one parenthesis. So here, we'll push the calculator. We'll push 1, 0 for 10, then divided by symbol. Push the sine button since it's in degrees mode. 6, 2. Your calculator probably has 2 parentheses already, but if it doesn't, then you have to put a closing parenthesis there. Actually, the TI-84 automatically closes it if you don't. But it's better to close it to avoid the risk that maybe you forgot one somewhere else and now it computes the wrong thing. So it's best to close your parentheses, make sure it's not making a mistake. And then finally enter to evaluate it. So this will take 10 divided by sine 62. And again, there is no cosecant button on most calculators, so you have to divide by sine instead of multiply by cosecant. Let's see what I get here. 10 times sine 62. And I get 8.8.
Yes, you're supposed to divide by it.
Right, and it said multiply, didn't I? I'm sorry, 10 divided by sine 62. Yeah, thank you. Just testing you, of course. Huh? I say that when I mess up. 11.326, rounded to 3 decimal places. And this, by the way, brings up something you should do when you're done. I said, always make a sanity check just to see if everything seems the right general size. Since I'm finding the hypotenuse C, this has to be longer than 10, right? So 8 can't be the answer. It has to be a number bigger than 10. This seems more reasonable, right? So we'll say maybe it's 11.326 is my answer. So you get one more side by the trig relation, whichever one relates to 2 numbers you know and one of them you don't. The second step then is you can use the Pythagorean theorem to find the last side. It is true that you can use trigonometry again to find the other side. There's nothing wrong with that. I'll give you full credit on the test. But usually it's easier to use the Pythagorean theorem. So I'll give you this cookbook approach, trig relation, Pythagorean theorem, just to save a little time. So since I have a hypotenuse C and one of the sides B, I'll say A is the square root of C squared, which is 11.326, minus B squared, which is 10. So what have we got here? The way to compute this, and this is another calculator hint, is to say, I might fat finger this if I type this in by hand, especially if I type more than this many digits. I'll probably make a mistake somewhere. So I can avoid that by instead pushing this second and the negative key down here at the bottom, right below the numbers. It's in parentheses for making negative numbers. Because above that, there's an ANS. This brings back whatever was the last answer on the display. In this case, 11.326, blah, blah, blah. So I'll push second answer when I want to get that one. And what I need to do to compute A now is push second x squared, because up above x squared is its inverse, the square root, right? Square root undoes the square. And a lot of these functions, you'll see the inverse function, the one that undoes something, is above the first one. So second square root puts the square root, and then I push second ands to get 11.326, and then I'll push the x squared button to square that, then I'll push the subtract, 10. On my calculator, I have to close a parenthesis. I have the parenthesis for the square root that's automatically inserted. And then push enter to evaluate it. So there's the keystrokes on this one. Take the square root of the display number squared minus 10, should have been 10 squared. We can push squared again. You know what, it might be easier than putting 10 squared. Let's push 100 because we already know what that is. Then put a parenthesis if you need it, and then enter. All right. So that's how you can do that one. And then we should say what comes up on the display. When you push this, for your information, what you get on the display is 10 slash instead of divide. This is the computer programming symbol for divide. If you're programming a computer, there is no key with that on there, so you just put a slash for divide. And then sign comes up and it automatically inserts a parenthesis. So even though you just push this, you'll see a parenthesis. And then 62 and the closing parenthesis. So this is what you'll see on the display, and then this number when you type these keys in. Similarly on this one, I think rather than memorize all those keystrokes, what you do is you remember what shows on the display. What it'll show on the display here is square root parenthesis. And then it will say ands squared minus 100, close parenthesis. So this is what you'll see on the display, and these are the keystrokes to get it. So try and get this on display, the first one, and this on display the next time. And what do we get for this one? Let's see. Square root ands squared minus 100. Oops, it's off. Always helps to have it on. Square root answer squared minus 100. Close your parentheses just to be careful. Now I get 5.317 approximately. Now I have all the sides, that's step 2. And then the angle is the easy part, right? Let's run this over each other. Let's see if I can split that up. And then finally 3. Trying to save this, but I just can't anymore. Getting too messy. Finally 3, you find the complementary angle. Alpha is 90 minus 62 degrees. The angle you're given is 28 degrees. So there's the 3 answers you see on the back of the homework list. Remember, the answers are there to check them. So there it is for given an angle and a side of a right triangle. Trig relationship relating the two numbers and one unknown to get the side. Use the Pythagorean theorem to get the other side. Use the complementary angle theorem to get the angle. Well, I said you can also do this if you're given two sides. And you can maybe figure out right away what the cookbook way of doing this is. Here's an example where you're given two sides. I like this example a lot. Suppose I'm given a triangle with sides 3, 4, and that's it. You can probably guess the first part of the answer on this one. That's what makes this kind of nice, is it kind of gives you a hint to do on what to do on all the others. And suppose this is beta, and this is alpha, so this is A, and this is B, and this is C. Solve this triangle. When you're given two sides, start off with the Pythagorean theorem. All right. The hypotenuse is always the root sum square of the other sides. Here's the Pythagorean theorem solved for the hypotenuse. Square root of 3 squared plus 4 squared. And you probably remember this one, right? Square root of 9 plus 16 is square root of 25. That's 5. It's a 3, 4, 5 famous triangle, right? But you can do that whenever you're given two sides, even if it doesn't come out to be a nice whole number. The second step when you're given two sides now is to use trigonometry to solve for one of the angles. And here's the hard part. You find an angle, either one you want, by inverse trigonometry. What's that? That's finding the angle from the side ratios instead of the side ratios from the angle. So there's a button over your sine button, just like the square root goes over the square button to undo the square. Over the sine button, there's an inverse sine button to undo the sine. And so if we know here, again, a relation of two numbers and one unknown, let's say we want to use beta. Let's say tangent of beta is 4 over 3, right? Opposite over adjacent, you have to memorize. So tangent beta is 4 over 3. Once again, I relate two knowns and one unknown angle. Now, inverse trigonometry says what angle has that tangent? Well, there's an inverse function called the arctangent or inverse tangent that says if tangent beta is this number in any triangle, then beta is this inverse tangent. This always works for a triangle. On the unit circle, if you're not in the first quadrant, it doesn't work. But this always works in the first quadrant, and we'll talk about what to do otherwise later. The only angle in the first quadrant whose tangent is this number is this arctangent. So what do? We simply type that in the calculator. You type second tangent, because over the tangent button is the inverse tangent or arctangent. And then you can put 4 divided by 3, close your parenthesis if your calculator doesn't, and push enter. Right, and what shows up is inverse tangent 4/3 on the screen. So you're trying to get this on the screen. When I do that, I don't have to check degrees mode because it stays in degrees mode from before. I'll just push arctangent 4 divided by 3. And I find out it is approximately, at least, it rounds it, 53.1301, blah, blah, blah. And if I'm rounding to 3 decimal places like the other one, then I do this, I write 53.130, and I carry the 0 here because it's a significant digit. If I write this, people will assume I rounded to 2 decimal places. This shows that the 0 is significant. So there's beta, and then you can guess the last step, right? Once you have one of the angles in the right triangle, the other one is always easiest by the complementary angle theorem. So that's beta alpha must be 90 minus that. Once again, it's easiest to use the ands angle. Just put 90 minus second ends and get the whole subtraction with all the digits. 90 minus second ends. And I got 36 point, guess we can get it, 36.8698, and etc. And if I'm going to round this, what do I do? Well, this 9 is followed by an 8, so I have to round up and call this 70. So we'll say this one should be 36.870 to 3 decimal places. I don't know if the homework said to round to 3 decimal places, but I wanted to round it here just to make sure I show you the rounding properties. All right, so there's that triangle solved when I'm given 2 sides. Pythagorean theorem first. Use trigonometry to, inverse trigonometry to find one angle, and then complementary angles theorem to find the last one. Now what you can see is given a side and an angle or 2 sides of a right triangle, you can solve the right triangle, find everything. And in the special case of a special angle, special triangle, you can find the information exactly. Well, there's another thing we should mention here. Occasionally, this is not very common. Instead of giving you a side and an angle or 2 sides, you might be given a side and a trig function of an angle. Well, that works just as well. You can always use inverse trigonometry, right, the buttons to find the angle if you want, but it's not actually that necessary to do that. Let's do this other problem, which actually pretty early on the homework. Suppose I said this, if cosine of beta is equal to 4/5 and A equals 10, solve the triangle. So this time, instead of being given beta and A, I'm given cosine beta and A. Well, once again, you can take the inverse trig function, find the angle, but it's easier than that. Sketch the triangle and say, well, cosine beta is 4/5 and A equals 10. So if this is beta here, let's say, then A, this would be alpha, and this would be A equals 10, so I could draw it like that. Then I'll say, I know this side, and I know the cosine of beta, which relates this side to this one, C, and here's B. So I want to relate these. I'd say cosine beta, what I'm given, is adjacent over hypotenuse. Now I can relate the 2 numbers I've known in this trig relationship. So I'll simply say, without using the inverse trig, exactly 4/5 is equal to 10 over C. Now I can find C exactly. When you see this, there's again lots of algebraic ways to solve it. We can say reciprocal equals reciprocal. That's what I usually like to do. But somewhere along the semester, I just wanted to support this one and say, if you have a quotient equal to quotient, you can cross multiply, right? This times this equals this times this. That's another thing people like to do. So I'll say equivalently, same solution set, 4C equals 5 times 10 or 50. So C must be 50 divided by 4. Right, which is 25 halves. There's an exact answer. On the calculator, sometimes you do these with inverse trig, you get a rounded answer, and it says, instead of this one coming out exactly 12.5, if you do enough of these calculations, you can get 12.49999 or 12.500001 or something. So this makes sure it goes exactly, and there's not some building up rounding errors. I will take either 25 halves or 12.5. When you have a half like that, everybody knows that's an exact decimal. So I'll take either one of those answers on that one. Well, that's the step 1, is you relate the 2 knowns to an unknown by 1 again. It's just this time you have cosine beta instead of beta. So, same concept. By 1, relate 2 knowns to 1 unknown. Now, You got it, right? Because the Pythagorean theorem is the easiest way of the next step. We can say I have 10 for A, and I have 25 halves for C, so B, the remaining leg, is the square root of C squared minus A squared, is the Pythagorean theorem solved for B, is the square root of, I'm going to write it as a fraction, 25 halves squared minus 10 squared. If I write this decimal, it's always hard to figure out the exact subtraction, right? 25 squared is 625, that's divided by 4. 10 squared is 100, and then you have to say algebra. How do I do this exactly? I put them over a common denominator. All right, 100 as 400 over 4, right? Once they have the same denominator, then you subtract the numerator. 625 minus 400 is 225, all divided by the common denominator, 4. Well, 225 is the square of 15, and 4 is the square of 2. So the answer is 15 halves, or if you like, 7.5, since it's a nice, easy, obviously exact decimal. There's this triangle. I have one last thing. Is the other, well, actually, instead of saying, we can find the angles by inverse trigonometry now, but let's just leave it there. The problem just said find the sides. I guess I said solve the triangle. Let's do it then. All right, so there's the exact sides, and now to get the angles, I won't get those exactly, because usually, even if the sides are nice whole numbers, the angles are not. They don't go together, whole numbers with whole numbers. So finally, if cosine beta equals 4/5, in a triangle, the angle is just the inverse cosine of 4/5. So I run that on the calculator. It's already in degrees mode. And I get 36 point, same one I had over here. Let's just say 36.9 to 1 decimal place. And then alpha is 90 minus that. This time I had 4 steps because I was only given one side. I had to find the other angle and the other 3 things. So alpha is 90 minus this. Gives 53.1. Approximately. They're solving it given a side and a trig function. What happens now is there's also some applied problems here. For example, this is kind of a fun one here, number 11 on the homework. It says this: suppose a 23-foot ladder leans against a building. So that the base of the ladder is 80 degrees to the ground. Wonder how high the ladder reaches. Here's the trick to pretty much all the applied problems is you draw a picture.
Can you move the camera a little bit?
Oh, I'm sorry, yeah, I thought I had it far enough. Yeah, there you go, thank you. So it's an application, draw a picture if possible. Often that tells you a big hint. It's not real clear from all these words, right? They say a picture's worth 1,000 words. So here's the case. I've got a building. Always assume buildings are vertical, perpendicular to the ground unless I say otherwise. And the idea is I lean my ladder against the building, and it's a pretty tall one, 23 feet. But this side of the triangle is then 23. And I've given this angle is 80 degrees. Now I can see all sorts of stuff. I see immediately this one must be 10 degrees is the angle to the building, right? And again, this will be a right triangle because we'll assume level ground. And then what I'm asked to do is find this height here of the building. Put a suggestive letter like H. And when you sketch this, sketch with all given numbers. And the desired number. Put a letter for it, write a variable. Now in this case, we can apply trigonometry. We're given an angle and a side, so actually we can solve the whole triangle, but in this case, we're only interested in the side. So what you do is you relate the desired value to the given numbers. So you use trig relating desires to the given. What trig function out of equation 1 does that? I have an angle and its opposite and its hypotenuse, so I had to use sine, right? Opposite over hypotenuse. I can also use cosecant, hypotenuse over opposite, but then, right, cosecant isn't on the calculator, so I have to do 1 over sine to get it anyway. Let's just start with sine. So step 2, then I'll say the sine of 80 degrees is equal to opposite over hypotenuse is h over 23. This is easy to solve, right? Just multiply both sides by 23 and get 23 sine 80 degrees is equal to h. Run that on the calculator. And I get 22.65 approximately. So that actually didn't take up much height at all. That ladder is pretty steep up there against the building. When it is, you only lose a fraction of a foot here. And the units are always the same as the ones on the other measurements. Here's number 10. Suppose you have a lightning rod is at the top of the building. From a location 500 feet from the base of the building, an angle of elevation to the top of the building is measured to be 90 degrees. 36 degrees. One thing you want to pick up out of these applied problems also is some terminology. So, angle of elevation means the angle up from horizontal like a gun turret. So that's up like that. And now we can sketch this and we'll say, find the height of the lightning rod. Let's see. Oh, and the the angle of the top of the lightning rod is 38 degrees. So this one's a little harder because it's got more than one triangle. But that's applied problems, right? But the picture signs in these. What is the length of the lightning rod? Part of the problem is it just takes so long to write it down. Makes it hard just that way. Move this over a bit. Hope that's all around there. Let me know if you can't see some of this here. What do? It's an applied problem. Step one is you draw the picture, right? All the known quantities and what you're trying to find labeled with a letter. Again, a vertical building. There's a lightning rod right at the top. We could say its height is h, but we need h for the building, so we could call it something else if we want. Why don't we call it L? How about that? Length of the lightning rod and h, height of the building. Now what we do is we stand 500 feet in the distance, assuming a right angle here. Measure this angle up and get 36 degrees. Measure this angle up carefully and get 38 degrees. Now we see what's going on. How can we solve this one? There's a key feature going on here is that when you know two pieces of information other than angle, which is really only one, you can solve the whole triangle. So I know 500 feet and 36 degrees, I recognize immediately I can solve this triangle. Right? I can find anything I want in there. So what do I need? Well, one thing I might need is the height of the building, right? So I could say, because I'm going to think of this strategy. To find the height of the lightning rod, L, I'm going to take the height up to the top of the lightning rod minus the height of the building. So I'm going to find both of those. I'll find this height here from this triangle, and then this height here from this triangle, and I can subtract them. So that's the strategy. I'll say, first for the big triangle, the tangent I'm going to use because it's opposite over adjacent. Tangent of 38 degrees is h plus L, the length of this side. That's the opposite side of 38 degrees, divided by the adjacent 500. All right? Tangent equals opposite over adjacent. Now, similarly, if I take tangent of 36 degrees, it's its opposite side to the adjacent. That's h over 500. All right? So I can from this, I better move this camera on. From the first one, I'll say h plus L by multiplying both sides by 500 is 500 tangent 38. And that comes out to be 390.6 feet. And then we'll say from the second one, multiplying through by 500, h is equal to 500 tangent 36 degrees. Now I get 363.3. If I subtract these, h plus L minus h gives me L on the left. And on the right, I've got 390.6 minus 363.3. Looks like 27.3 feet, right? So there's that problem. A lot of these applied problems can involve more than one triangle. I think that'll pretty well cover it. Let's do one more of these. Just partly just terminology getting up. Does this one look okay? This is a little harder. But you start to see that this is really useful stuff. Again, if you get something that's not a right triangle even, you can often solve it anyway. Sometimes you get something like this. You got someone spotted at the top of a building, right? And you know how high the building is maybe, and maybe you know your distance between the two people. And you say, I wonder how high that building is. So you measure this angle and you measure this angle and you say, I know how far we are apart. You can actually solve this by dropping a perpendicular and making two right triangles. So even non-right triangles, it is possible with a little more work, since we have two triangles there, to solve two triangles by dropping a perpendicular. However, later in the semester, we will learn special techniques for non-right triangles that are faster than making mobile triangles also. But that makes this very powerful, because now by dropping perpendiculars, you can solve much more general problems. All right, so here's number 7. This is kind of a tricky problem also. It's got a plane takes off bearing 29 degrees north, 29 degrees west. For 2 hours. And makes a right turn of 90 degrees. And flies 15 miles per hour. Oh, this was 9 miles per hour. This is a model airplane or something. All right. So it travels this one for 2 hours at 9 miles per hour. Then makes a right turn 90 degrees, flies 15 miles per hour for 3 hours. What is the bearing of the plane from its starting point? This one you just about have to draw a picture. This means from north, go 29 degrees to the west. So you have this kind of a thing in the coordinate system. You turn 29 degrees, about a third of a right angle, right? Like that. And here's the bearing it starts off at. And it travels for 2 hours at 9 miles per hour. So you take 9, this distance here, T1 if you like, is 9 miles per hour. You can also write miles per hour as mph, but if you put it this way, then you can cancel the units. Right? 9 miles per hour times 2 hours. Now the units cancel and you get 18 miles. So the plane has traveled 9 times 2, 18 miles. It makes a right turn Which way did it turn? I'm sorry. A right turn. So it goes like this. Now it flies 15 miles per hour. For 3 hours, out this way somewhere. And then it's got a final location. You're asking, what's the bearing up there? So this side here, D2, is 15 miles per hour times 3 hours. The hours cancel and you get 45 miles. So this is a 45, this one, 45 by 18 by something triangle. And we want to know the bearing of all things. How about that? So the bearing is actually going to be this angle north so many degrees east. So if I just find, let's say, this angle of the triangle, I can subtract out 29 degrees and find out what this angle is. So if I call this alpha arbitrarily, then this is A, and then this is beta and B here, I can try and solve this triangle for alpha. I'm given two sides in this problem, so I can say the trig relation relating the given numbers, 18 and 45, to the unknown angle that I want, alpha. But that's the idea of this. You write down all the numbers you know and the one you want to find. Right? Well, let's see. These are opposite and adjacent to alpha, so I'll say tangent of alpha by equation 1 must be 45 over 18. Right? Well, if the tangent of alpha is 45 over 18 inside a triangle, alpha is always the inverse tangent or arctangent of 45/18. And an important thing on these inverse trig functions, if you leave your calculator in radians mode, it'll give you the answer in radians. If it's in degrees mode, it'll give you the answer in degrees. So make sure it's in degrees mode here. And we'll take second tangent, right, to get the inverse tangent. 45 divided by 18. That fraction reduces, but we don't need to since we're taking arctangent. This comes out to be approximately 68 degrees. We'll just round it to the nearest digit, assuming this one was. And so consequently, the angle over here we have here 68, well, 68 less 49. Sorry. Gives us 39. And you can say, therefore, since this is turning west 39 to east 39 degrees, this is the bearing is in north 39 degrees east. I'll do that one. So kind of a tricky problem there.
Did you mean to do 3 hours on the word problem part of it? Because on the homework it says 3 miles.
Oh no. Well, it's not going to give the same answer as your homework then. It's probably a typo on here. This one says makes a right turn with 90 degrees and flies at 15 miles per hour for 3 hours. Yours says 3 miles?
When I printed it out, it said 3 miles. I'll change it.
That's what it says on the handout I put on D2L. Maybe I put an old one with some typos in it. I'm worried. It should have been 3 hours there.
Yeah.
Okay. Well, that's it. That's all the triangle stuff we want to do. As you can see, this is some of the more important material of the semester. The next topic then that we just talk about real briefly, and we'll do more with it next time. I have a nice picture to put up. I wasn't expecting to do any of it today, so I didn't quite. I don't have it up yet, but we can introduce this a little. These graphs of sine and cosine. You can get these from the unit circle again. If you take the unit circle and consider running an angle in standard position, so here's the angle theta. What you have is, again, sine is a function, right? It's the y coordinate corresponding to the angle theta. So you put in one angle theta, you got one y coordinate, that's a sine. So we can do this for all our special angles. And say, in particular, when we have a 0 degree angle, let's mark this again. The first coordinate is cosine, the second coordinate is sine. We'll say from this, compute all these special angles. I showed you that picture on the overhead before where it has them all figured out for you already. At 30 degree angle, we already know the coordinates of points, a 30, 60, 90 triangle. So this is square root 3 over 2 on x and 1/2 on y. Right? At 45 degree angle, we have square root 2 over 2, square root 2 over 2. Right? At a 60 degree angle, we have this point, 1/2 square root 3 over 2, because now the 30, 60, 90 goes this way. At 90 degrees, you get the point 0, 1. And over here at 0 degrees, you get the point 1, 0, and you can keep going. Remember, in the other quadrants, you get the same reference triangles. So here you get -1/2 plus square root 3 over 2, because you went left and up, but it's the same triangle as this one. Is there a question? So that's that point there. And then this one is correspondingly minus square root 2 over 2 plus square root 2 over 2. And you keep going around the triangle like this. This one is -1, 0. And you can build up a table, right? There's a really neat picture that I'll show you next time on Wikipedia if you look up these things. But it looks like this. Now you can make a table of theta versus y equals sine theta. Right? Y coordinate is sine of theta. When theta is 0, the sine is the y coordinate is 0. But when theta is 30 degrees, let's call that pi over 6 and use radians, and call this one pi over 4, and this one pi over 3, and so on. So then pi over 6, that's just the way people usually graph them. Comes out with sine is 1/2. Pi over 4, 45 degrees, gives us square root 2 over 2. Pi over 3, 60 degrees, gives us square root 3 over 2 for the y coordinate. And 90 degrees, the sine is 1. So at pi over 2, you get 1. And then you can keep going, right? You can go all the way around the circle. And even further, right? You can go around over and over and over. If I put 2 pi over 3, I mark that one. At 2 pi over 3, this one, then the sine is the y coordinate here is again square root 3 over 2. So it starts coming down in the same way. At 3 pi over 4, this angle, well, that was this one. I didn't mark it, but there it is. The y coordinate is square root 2 over 2. And so on. So it starts repeating these numbers, you notice. At 5 pi over 6, it goes down to 1/2. At pi, you get this point, -1, 0. Evidently, the sine is equal to 0. So you can now sketch that, right? You can take a graph of theta versus y equals sine theta and say you plot the point 0, 0. You plot the point pi over 6, 1/2. Here's 1 up here. Let's say. So halfway up there would be about like this. Square root 2 over 2 is a little bigger. At pi over 4. Square root 3 over 2 is like 0.87, something like that. It's pretty close to 1 at this point. That'd be a pi over 3. So I plot x equals pi over 3, y equals this. And at pi over 2, 90 degrees, I plot 1. Right? And if you do more calculator numbers, you'll find out that you can fill in between all those dots that we know exactly. You get a curve nice and smooth that looks like that. And now it starts to come down in the same old fashion, right? At 2 pi over 3, it's back down to this number, square root 3 over 2. Here's square root 2 over 2. Here's a half, right? And so we plot all these back again. This one, and then at 3 pi over 4, 5 pi over 6, and pi. And at pi, it gets back down to 0, and it looks like this. It looks actually nice and symmetric. It goes down exactly the same way it came up. Well, if you keep going, here's 7 pi over 6. You go 30 degrees past a straight angle. Again, you got a 30, 60, 90. Now the coordinates of the pointer are minus square root 3 over 2 minus a half. And the sine coordinates for all these angles start to get negative. This one is now minus square root 2 over 2, minus square root 2 over 2. And so you can keep filling out this table. All the way until you get back to 2 pi. And at 2 pi, sine is again equal to 0. And what you find out is these numbers are, look, they're just a negative of these numbers going backwards. And so this looks exactly symmetric, but the y coordinates are negative. And at 2 pi, it gets back to 0. There's the graph of what we call one period of the sine function, because now what happens is if you go more angles, you start repeating the y coordinates. After 2 pi, it just repeats. Every 2 pi, you go around, it repeats. So if you keep graphing it for larger angles, it just goes up in the same old way, back down in the same old way, and back to the beginning. And when it gets down to the second rotation, that's at 4 pi. Right? And so it keeps going like that. And it repeats over and over. You can do negative angles, so it goes this way. And what you get is what's called a sine wave. This is the graph of y equals sine theta. It oscillates up and down between y equals plus and minus 1. There's the crest. There's the bottom of the valleys go down to minus 1 is the lowest value. It's a wave that goes up and down, repeats every 2 pi units. We say it's 2 pi periodic, or has period 2 pi. And now we just need to do the graphs of the other trig functions. And in practice, this is the kind of thing you might get from a radio signal or something. You might have a higher frequency, so you might maybe not just want sine theta, but maybe now what's the graph of sine 2 theta look like, or those kind of things. But this will get us started. This is a really important concept in lots of the sciences, to be able to do things with waves. They're involved in vibration analysis, traveling radio waves and light and all sorts of things like that. Try all the problems in on 5.4, the last section, I think it's 5.4, on the triangle. And yeah, 5.4, just do all the problems on the UCO supplement except the last one, I think. Let's just do 1 to 11 out of the supplement. See if you have any questions on that for next time. There's a bunch of good applied problems in there. We did some of them. Thank you. See some of you on Tuesday then.
Thank you.
Thank you.
Thank you. Have a good day.